All right, so this is the last section in Unit 3, and this is the applications of exponentials and logarithms. So unfortunately, and I'm just going to apologize, the entire section is story problems, every little thing. In most of the stories, they'll give you the equation, but there are going to be some where you're just going to have to write it. And so this is going to be very calculator heavy as well because these aren't going to be very nice numbers. But the good news is you will get more practice solving these types of equations. And so hopefully that helps with the last few sections as well. All right, so here is the first one, and these are all my open math questions. So these should all translate directly to some of your homework problems. It says the value of China's exports of automobiles and parts, and it says in billions of dollars, is approximately, and they give an equation where x equals 0 corresponds to the year 1998. In what year did/will the exports reach 7.4 billion? And so this 7.4 billion is not the X value, it is the Y value, and it's in billions of dollars. And the question is in what year did it get there? Where X is talking about the year. And so what we're going to do is we're going to set this equation up and we are going to solve for X. All right, so the nice thing is they already gave us half of the equation. The other part is that it's just equal to 7.4. So 1.8208 E 7x. There we go. All right, and we're going to go ahead and do some solving here. So the first thing you can do is you can divide both sides by 1.8208. So we're going to do that division. And when you divide, it's probably best to take it to 3 or maybe 4 decimal points so that you get a pretty accurate answer at the end. So I have 4.064, and so I'm going to take it that far, equal to e to the 0.3387x. All right, and then the next step, when you have something in the exponent equal to a number, we've talked about in 2 units ago when we were solving exponential equations, that you can take the natural log of both sides or the log of both sides. It's up to you. And what happens is this exponent moves down in front. You're using the power rule. And so what you're going to see on this side is you're going to see 0.3387x times the ln of e. And hopefully by now, maybe you're recognizing that the ln of e is just equal to 1. So that's 1 times this, which is just this, right? So that ln of e is going to go away completely. So on this side, you're just going to have the decimal times x. In your calculator, you're going to calculate the ln of 1.4, sorry, not even close, 4.046. And you're going to have 1.402 approximately. So we'll say 1.402. All right, and last but not least, you can solve for x by doing one more division operation here, dividing by that 0.3387 decimal. So using your calculator, I have that x would be equal to 4.13, and it rounds. I have 0.1398, so that would round that to a 40 at the end instead of 39. So 40, approximately there. All right, and so then we have to go back and make sure that we answer each of the questions. So we got a value for x, but the question says in what year? So does it make sense to say that in year 4, it's saying specifically what year? And it did tell us when x is 0 corresponds to 1998. So what we can do is we can take 1998, add 4 years to it, and that's going to happen in 2002. So the year would be 2002. All right. Up next, We have the current student population at a college is 8,800 students. If enrollment is projected to increase at a rate of 2.75 each year, what will be the student population in 13 years? Part A says write a function using t for the number of years. And so we're not going to use x, we're going to use t. And then part B says what is the population in 13 years? And that says round to the nearest student. So that'll be the whole number. Now, unfortunately, they don't give us an equation because they want us to write it. And this is just an exponential growth equation. And what you're going to do is you're going to start off with 8,800 students. And this is going to be multiplied by the rate. And here's where you have to get kind of careful with your rate. For starters, it's a percent. And so that would be 0.0275. Remember, you can divide it by 100. But what's going to happen is if you do this times this you're going to get a smaller number. That number is going to go down. But what's happening is it's actually increasing. And so what you have to do is you have to put a 1 in front of this number. Essentially, you add 1 to it to say, hey, keep the original amount, that's the 1, and then increase by the 2.75%. And so after the first year, you would just times this once. If you're doing 2 years, you times it once and then you times it again. If you were doing 3 years, it'd be multiplied by this 3 times. 4 years would be 4 times, 5 years, 5 times. So the number of years is the exponent, how many times you multiply by this value. So there is your equation. Remember, you're supposed to put in t and not x. And then it says, what will the population be in 13 years? Well, 13 years means that you take the t and you plug in 13. So the nice thing is we're not figuring out, or we're not saying it's equal to 13 and we're having to solve. We're just plugging in 13. So in your calculator, you can go ahead and calculate that value. So it'd be 8,800, 1.0275 raised to the power, and that's the caret button. I don't know if you can see it there, caret button. And the power is 13 years, so the power of 13. And so that's going to be 12,521.2. And they said round to the nearest student, so that would round down to just stay at the 21. So 12,521 students. All right, so that one a little bit more complicated because, yes, you had to write the equation here. But you're using exponential growth in this case. All right, here is the next one. A computer purchased for $1,350 loses 18% of its value every year. The computer's value can be modeled by the function v of t equals a times b to the power of t, where v is the dollar value and t is the number of years since purchased. And then it says, in the exponential model, so in this model, what is A and what is B? So what they're really saying is write this equation and tell us what number you put in for these two values as opposed to just writing the whole equation. All right, so let's go ahead and say the initial amount, right, is $1,350. And then it loses 18%. So the last problem was increasing by 18%. This one's losing 18%. So you're going to have the 0.18, but this time it's losing. So instead of adding 1, you actually subtract it from 1. And so that would be 0.82. So it's 1,350 times 0.82 to the power of t. How many years? So it's either the percent plus 1 or the percent being subtracted from 1. It will pretty much hardly ever be the actual percent just as it is. So in this case, your A is 1350 and your B is 0.82. All right, so this is part A. We got that equation there. Part B of this problem says, in how many years will the computer be worth half its original value? And then it says round to 1 decimal place. So half of its original value is how much? Well, if it's originally 1350, you can divide that by 2. And so half its value is 675. So we're going to take our equation and we're trying to find the time that this equals 675. So this will be 675 equal to our equation here, and we are solving for t. All right, this one will solve just like the question above it. So if you want to pause and try to solve it on your own, feel free. I am going to do it with you though, but if you pause and then come back, you can at least check and see how you did, where you made a mistake at. All right, so up first is the division. So you're going to do 675 divided by 1350. And then you will get 0.5. And there is a relationship there because it's half and half is 0.5. So it should work out if you're ever working with halves or doubles that you get 0.5 or 2 going on there. All right, from here you have something raised to a power. And so the strategy here is you can take the natural log of both sides of this. And then what's going to happen is that t will come out of the power and drop to the front. So you have the ln of 0.5 equals t times the ln of 0.82. And then last but not least, you can solve for t by dividing by the ln of 0.82. And so that will tell you what t equals. And so we're going to go ahead and type this into our calculator. So the ln of 0.5, make sure you close that parenthesis, divided by the ln of 0.82. This one you can close or not close. It's completely up to you. 3.49. And it says round to 1 decimal point. So 1 decimal point would be 3.5. So it's approximately 3.5 years. All right. So we pretty much kind of summing it up. We had one where they gave us the exponential equation. We just had to solve it for a specific value. And then they gave us an exponential growth and an exponential decay type questions. And so if you see anything that are talking about like increasing exponential growth or decreasing exponential decay, there's your examples of each of those. And so what we're going to see for the last few problems is we're going to see another very practical application of exponential functions, and that's compound interest. And so this is a formula. This would be great for your formula sheet. So would this one. But what these are is they're just formulas that will tell you if you invest a certain amount of money in a bank and they give you a rate, a return on your money, and they compound it. So compounding is like how many times the bank calculates the interest. And so they'll compound it a certain number of times. This formula will just tell you the outcome there. It'll tell you the amount that you would have in the bank. And then the compounding continuously is a play off of this formula right here. But the difference is instead of it like compounding a certain number of times, it's just always compounding its interest. So it's always calculating the interest there. So this is like the ideal in like a perfect world. This is what we would like to see happen, and you would make the most money with an account like this. But this is more of a reality of how things are calculated. And so the only difference that you're going to see between them, the main difference is you're going to see this word, the word continuously. So if you see continuously, you should use this one. If you see any other word besides continuously that talks about how often it compounds, you're going to go with the first one. All right, so I have 2 examples of these. So it says if $19,600 is invested at an interest rate of 8% per year, find the value of the investment at the end of 5 years for the following compounding methods. Round to the nearest cent because we're talking about dollars. So if you compound annually, that is once per year, right? Annually would be once per year. Semi-annually would be twice per year. Monthly is going to come in at 12 times per year, and then daily 365. We're not going to mess around with the whole leap year, not leap year. There's actually like an extra 25.25 in the year, but it's just 365. This is also information that you might want to write down if you don't know those numbers. specifically the daily. Most people know there's 12 months in a year and things like that. But if you don't know how many days are in a year, that might be a good, like, hey, throw it on there just in case. All right, and so here's how this formula is going to work. None of these are compounded continuously. They're compounded a certain number of times. And so we're going to be using the first formula. We're going to use this formula every single time. So the amount that we'll have in the account will be equal to the P, which is the principal, the initial amount, 19,600, parentheses, 1 plus R, and R is your rate, and it says 8%, and like all other rates, you put it as a decimal, over N. N is the number of times it's going to compound. So for problem A, for part A, it's going to compound once. Close your parentheses, and then it's to the power of 1 times the time, how many years we're going to do this for. So we're going to do this for 5 years. And so you are calculating this value right here. The good news is you can type this into your calculator in one shot. You don't have to split it up into a bunch of different things. So 19,600, parenthesis, 1 plus 0.08 divided by 1, close parenthesis, to the power of, and here in the power, you should go ahead and just multiply them in your head before you put them in there. So 1 times 5 is just 5. If you're going to do 1 times 5, you should put parentheses around it, but 1 times 5 is just 5, and that really helps out. So we have $28,798.83, because it's 83.0, so 83 cents. All right, so that would be your answer for part A. Part B is the same situation, but this time they're going to compound it twice, semi-annually, twice a year. So it's the same starting amount, still 1 plus 0.08 over, and in this time it's over 2, because instead of compounding once, it compounds twice, and then to the power of 2 times 5, so that'll be the power of 10, and we'll say what that equals. If you hit up on your calculator, it should let you go back through, so you don't have to retype everything. And when you get to the one there, you just change it to a 2. You don't hit delete, don't hit clear, just hit 2. And then here at the 5, we're going to change that to a 10. And no delete, no clear, you just start typing over at 10. All right, $29,012, and this is going to round to 79 cents because of the 7 at the end. That'll round that up to a 9. All right, part C. Now we're doing the compounding monthly. So everything else exactly the same, except for the 2 changes to a monthly. So this will be 12 times 5 in the power there. 12 times 5 is 60, right? 60. So just hit up and you should be able to go back through and make some changes. So this 2 should become a 12. When you do that, though, at that number, you kind of just have to parenthesis and rewrite the rest of it, because it throws it off on it doesn't move it over. Like if you put an extra letter in Microsoft Word or Google Doc or whatever, it just moves everything over. In the calculator, it just replaces it. And so when you change that 12, you'll have to put your parenthesis and raise it to the new power. And you should have 29,298 for this one. All right, and last but not least, same thing, but this time we're doing 365 times, so it does it once a day. Ooh, the power is 365 times 5. So I don't know what that is off the top of my head, so I'm going to have to put parentheses in my calculator when I do it. So hit up, go over. When you get to the 12, you're going to change it to 365. Close the parentheses, raise it to the power of, and then I'm going to put parentheses 365 times 5 because I don't know what that is. So I do have to put it in parentheses there. 29,238.48. All right, so there are your values for all of these. Notice that as you compound more often, the values go up. So once versus twice, 2 versus 12 times versus 365. And so when you get to where it's doing it more than 365, it's just a continuous, that's when you get to the other formula. And that's where that E pops out at. All right, so we do have some compounding continuously questions going on here. So let's take a look at those. It says, find the time it takes for $8,900 to double when invested at an annual interest rate of 2% compounded continuously. So I'm going to call this part A. I'm going to be part B. So for part A, we want $8,900 to double. And if it doubles, 8,900 times 2 becomes $17,800. And so for part A, we're going to use this formula right here. PE to the RT is equal to the amount. So your amount is 17,800 equals P, the original amount, 8,900, E to the RT, and R is your rate, 0.02. And then we are trying to find the time, so we'll have T in there. And this is the equation that we are going to have to solve. So first step, divide by 8,900. By the way, that should be 2, right? 0.02 to the T. And then here we are again, we have a variable in the exponent, and we need to solve this. And so the strategy here is to take the natural log of both sides, because when you do that, this power will be able to drop down to the front, and the 0.02t is no longer in the exponent. So this side here will be 0.02t times the ln of e, and the ln of e is just 1, so you can just leave it off. If it's the ln of anything else, you include it. And then that equals the ln of 2. And then you can go ahead and just divide by 0.02. So the time here is going to be equal to ln of 2. Make sure you close the parentheses before you hit divide by 0.02. We have 34.657. Does it say round? It doesn't give me a decimal point to round to, so I'm just going to go to 2 decimal points. So I'm going to say 66 for that one. All right, for part B, it says find the time it takes for 890,000 to double when invested at an interest rate of 0.02, compounding continuously. So it's the same general setup, but now we're dealing with a lot more money, right? So what you can do is you can set it up like this, or you can, if we're already doubling, what it's really going to be is 2 equals e to the 0.02 t. You'll be at this line. Because it doesn't matter the amount that you start with, right? If it doubles, when you do the division, you'll always get 2. And so technically this question is the same as this line, isn't it? And so we should expect to get the exact same answer there, because we had 2 equals e to the 0.02t, 2 equals e to the 0.02t. So it doesn't matter how much money you're putting in there. If you're doubling it and you have the same rate every single time, then you should expect it to be the same amount of time. So this is also 34.66 years. If you didn't recognize that, you could go through all of the math there and you would get the answer just like you did for part A. All right, last one. So we have a certain radioactive isotope has a half-life of 75 days. How long will it take for the radiation level of a certain sample of this isotope to drop to, and then half of its original value and 1/16 of its original value? So the first question is kind of like a trick question almost. It says its half-life is 75 days. And so that means after 75 days, you're going to have half of what you originally had. And so if you have 75, or if you have an amount and you're looking for when half of it is that's after 75 days. Kind of a trick there. All right, the next one, not so easy. You might be able to try to figure out what's happening here because it's 1/16th, and there's a relationship to 1/16th and a half. But I don't know, it might throw you off. And so here's a formula for half-life. So this would be a good one to add. So your amount at the end is your initial amount. So we just call that a sub 0. So initial amount at the end. 1/2 is your rate because it's a half-life. And that's your time over how many days, what the half-life is actually. And so we want it to get to its 16th of its original level. And so what we can do here is we can pick in a random amount. So we're going to pick an amount so we have all the numbers that we need, and we're just going to go from there. So I'm going to pick 16 because it's really easy to figure out what 1/16th of 16 is, and that's just 1. So your final amount is 1. Your initial amount is 16, and then you'll have 1/2 to the power of t divided by the half-life, and the half-life is 75 days. All right, so we need to solve this equation for t. So first step, divide both sides by 16. 1 divided by 16 is 0.0625. Will be 1/2 to the power of t over 75. From there, we're in this situation again where we have a variable in the exponent. In order to get it down, you have to take the natural log of both sides, and that'll move this t over 75 down. So we'll have the ln of 0.0625 equals t over 75 times the ln of 1/2. And I'm just going to write ln of 0.5 instead of 1/2 because the fraction might make it look a little bit more complicated for you. All right, and then we're solving for t. So the first step that I would do is I would divide by the ln of 0.5. And over here we'll have t over 75. And so let's calculate that value. We have the ln of 0.0625. Make sure you close that parenthesis. Divided by the ln of 0.5. And so that is equal to 4. And so last but not least, you have to get rid of the divide by 0.75 by timesing. And 75 times 4 is 300. So after 300 days, we will be to 1/16th of our original value. All right, so once again, this would be a good one for half-life, maybe throwing that on there and then putting an example in your notes as well. Let me know if you have any questions on the homework problems. I am here to help.